All right, engineers, welcome. If you've ever set foot in a refinery, a power plant, or pretty much any big industrial facility, you've been surrounded by shell and tube heat exchangers. They're the real workhorses, the unsung heroes of process control. So today, we're going to do a deep dive. We're talking about how to design one from the ground up using the two big rule books, TEMA and ASME. We're going to tackle this just like you would on our real-world project. First, we'll pick the right configuration. Then we'll figure out how big it needs to be, design all the internals, choose the best materials, and finally, we'll pull it all together with a real-life industrial example. So, let's get into it.
First things first, we have to speak the language. And when it comes to heat exchangers, that language is all defined by the Tubular Exchanger Manufacturers Association, or as everyone calls it, TEMA.
What TEMA gives us is this simple but incredibly powerful system, a three-letter code that spells out the exact mechanical build of an exchanger. And this isn't just for convenience, it's a universal language. It means an engineer in Houston can specify a BEU type, and a fabricator halfway across the world in Singapore knows exactly what they need to build. No confusion, no mistakes.
So let's break that code down with a super common example, the BEU type. The B tells us about the front head, in this case, a bonnet head. The E is the shell type, just a simple single-pass shell. And the U is the rear head, which tells us we've got a U-tube bundle. Now this U-tube design is really clever, especially for maintenance. Since the tubes are bent in a U and only attached at one end, you can pull the entire bundle right out of the shell. This makes cleaning or repairs so much easier, a huge win in services where you know you're going to get a lot of gunk building up.
So, we've picked our BEU configuration. Now the big question is, how big does this thing actually need to be? To answer that, we've got to calculate the total heat transfer area we need.
You know, one of the biggest challenges here is that the temperature difference between your hot and cold fluids isn't constant. It's always changing as the fluids flow through the exchanger. So how on earth do we get a single, usable number to work with? Well, that is exactly where the log mean temperature difference, or LMTD, comes into play. It's basically a special kind of average that gives us the true driving force for heat transfer across the entire unit.
Okay, so the calculation itself? It's a four-step deal. First, you find the temperature difference at each end of the exchanger, then you plug those into the LMTD formula. But hold on, there's a catch. For those multi-pass designs like our BEU, the flow isn't just a simple straight line. To account for that more complex flow path, we have to apply a correction factor, F, which you can look up in standard TEMA charts. That gives us our true corrected temperature difference. All right, let's move inside the exchanger and look at how the physical layout of the tubes and baffles is actually engineered to squeeze out maximum performance and reliability.
So one of the first mechanical decisions you're going to make is how to arrange those tubes. A triangular pitch lets you pack in the absolute maximum number of tubes, which is great for boosting heat transfer. But it creates these really narrow lanes that are a nightmare to clean. On the other hand, you have a square pitch. It's less dense, sure, but it gives you these nice clear lanes for mechanical cleaning. Now, if you're in a refinery dealing with dirty crude oil that you know is going to cause fouling, that ease of maintenance often makes the square pitch the winning choice, even if it means you end up with a slightly larger shell. It's all about trade-offs.
Now let's talk about the baffles. Their whole job is to force the fluid on the shell side to flow across the tube bundle, not just along it, which is way better for heat transfer. And TEMA gives us a really handy rule of thumb for how far apart they should be, somewhere between 20% and 100% of the shell's inner diameter.
And the reason this spacing is so critical is that it's all about finding the right balance. You see, if the baffles are too close together, you create this long winding path for the fluid, and the energy you need to push it through, your pressure drop, just goes through the roof. But if they're too far apart, you get these dead zones where the fluid barely moves, allowing all that dirt and gunk to settle out and foul up your exchanger.
You know, a heat exchanger is only as good as what it's made of and how well it can handle the tough realities of industrial service. So let's talk about designing for durability.
The choice of material is 100% driven by your process conditions. For something non-corrosive at moderate temperatures, good old carbon steel is the workhorse. As things get hotter, we switch to chrome moly alloys for that high temperature strength. For general corrosion resistance, stainless steel is the go-to. And for really aggressive stuff, like seawater full of chlorides, you need to bring out the big guns, like duplex stainless steel, which is fantastic at resisting stress cracking.
Fouling is pretty much the arch nemesis of every single heat exchanger out there. It's just the buildup of junk.
scales, sludge, whatever, that forms this insulating blanket right on the tube surface. And that layer directly fights the flow of heat, which means your exchanger's performance is just going to get worse and worse over time.
Now, to fight back against this inevitable drop in performance, engineers design in a safety margin. TEMA actually provides standard fouling factors that we build right into our calculations. So for a really clean service like steam, that factor is tiny. But for a really dirty service like refinery crude, we have to add a significant amount of extra surface area just to make sure the exchanger can still do its job months down the line when it's all fouled up.
And it's not just about fouling. We also have to design to prevent other common ways these things can fail. If your fluid velocity is too high, you can get erosion, especially right at the tube inlets. Unsteady flow can cause the tubes to vibrate and literally wear themselves out against the baffles. And for some materials, like stainless steel, if you have the wrong mix of chlorides and temperature, you can get catastrophic stress cracking.
All right, time to put all these pieces together. For our last section, we're going to walk through a complete design for a classic refinery application: cooling down hot crude oil with cooling water.
So, here are our design parameters. We need to cool crude oil from 180 degrees Celsius down to 120. We're using cooling water that's going to heat up from 28 to 45 Celsius. We've got really strict limits on our pressure drop, and we've picked stainless steel tubes to handle corrosion. And just like we discussed earlier, a BEU type is a really good fit for this job.
The first and honestly most important number is our heat duty, which we call Q. Based on our flow rates and temperatures, we need to move 2.5 megawatts of thermal energy from the crude oil over to the cooling water. This number drives absolutely everything else in the design.
And this right here is our core engineering toolbox. We use that heat duty and our corrected LMTD to figure out the surface area we need. Then we double-check that our fluid velocities are high enough to create turbulent flow. That means a Reynolds number over 10,000, because that's essential for good heat transfer. And finally, we turn to the ASME pressure vessel code. We use the hoop stress formula, which connects pressure and diameter to material stress, to calculate the absolute minimum wall thickness we need for our shell end tubes to safely handle the pressure.
So there you have it. From TEMA types and LMTD calculations all the way to baffle design and material selection, we've walked through the entire design process. You now have the fundamental building blocks to go out and tackle any shell and tube exchanger design challenge.